Welcome to another lecture of GIS, the favorite part of GIS, its uniqueness. That is, we are going now moving towards analysis. And today the lecture is on spatial queries in geographic information system. I am Dr. Seema Mehra Parihar. I have been teaching remote sensing and GIS for last 30 years in Kirodimal College, University of Delhi. I have had my sharing of learning from IRS Dehradun and had my postdoc from ITC Netherlands. I've done my PhD from Delhi School of Economics, Department of Geography, and I'm using GIS in my research related activities. That is my different projects. So today we are going to learn about the first step of data analysis. In this chapter you learn the following. Number one, you will be able to evolve linkages between database structures and multiple spatial queries, appreciate the classification of queries, be able to understand the basics of thematic query, geometric query and topological query, and also you will be able to recognize the relevance of spatial dimensions based query in decision making of all kinds. It's just that simply one word called queries. You will learn that. And by now people have learned the meaning, relevance and power of GIS. You've also learned the advantages of GIS. You've also learned about the raster and vector GIS, how they are different, and the storage and the compaction ways that they're done. GIS largely is a decision making tools. And what does that mean? That means we ask queries, we ask questions, we can question GIS and get result. So GIS is a query based spatial data management system, one theme line, and this lesson deals with the different aspects of spatial queries. The aim of spatial queries and their analysis is to detect spatial relationships between elements of one or more subjects in order to locate spatial objects. The result of such analysis can be used in decision making. The database structures which is included in GIS enable the logical, consistent and ordered storage and management of data we learned in the previous chapter. So both thematic and geometric information are stored in the forms of tables. And in the discipline of geoinformation, the term data analysis includes all those investigations, queries, evaluations, etc., which are carried out in a structured and stored spatial data. And when a query is performed to obtain answers to a spatial question, the data are accessed through the basic elements of the structure, which is made up of tables, fields, data sets, values and connections. We all know it. The simplicity or the complexity of a query many a times is also guided by the available software capabilities. But foremost of this is the user's requirement and understanding of the capability of the geographic information system. And the following section deals with the kind of queries that GIS can handle or can handle, will handle and should handle. And this figure which you are seeing now on your screen is a query based spatial data management system with multiple layers. You know the strength of GIS, multiple layers, lot of data, spatial and spatial, and query is a step towards information system. And as Bill says, it's a deduction of new information from existing spatial data is one of the main tasks of a geoinformation system. Spatial analysis comprises of analysis and synthesis of spatial data to a unity, and every spatial analysis implies the professional interpretation of the results and ultimately leads to decision making. Through GIS, what you need to build is a multiple queries that are revolving around unique system, where a question and answer system are designed in a system which is a repository of data set. We know by now that the spatial information system deals with tools, algorithm and technologies in a computerized environment through innumerable queries. So tool, algorithm and technologies. This enables handling of large data sets and conversions of raw data into useful information. System is also called a geographic information system if the data are geographically referenced. GIS is composed of various individual components, and some of these functions are basic while others are complex. Depending on the data set, depending on the objective, depending on what you want to do, depending on what type of information you want from the spatial data base in which is stored in such a structured way. This also, the users also start getting a lot of operations can be performed, the functions can be executed and a lot of data can be accessed. And the data access and data management in general is controlled by the database management system. And as depicted in the lesson below, before what you've done, the computer-based decision-making system which is there is the case of in a GIS what you find. There are two types of data which are there, spatial and spatial, or what you call an attribute data. And all query based on existing spatial and spatial data are based on your requirement. And the data structure comprises the association of theme-driven thematic data and spatial-oriented geometric information. Certainly, geometry is expressed in the context of reference that has spatial connotations. What is important to understand is that the spatial reference is designed to allow all the objects, area or phenomena that one wishes to map. Of course, you are getting a remote sensing imagery and you want to map, but we have to take care that there are varied scales, there are varied what do you call a lot of things which are there which may have varied dimensions. We have to take care of that. So, that is the base. So, now let us talk about the classifications of queries. One is the based on the spatial and spatial relations. I hope you are understanding. You have spatial relations and you have spatial relations. Spatial relations are, say it's a Delhi region, you got a lat long 76 degree, 10 minutes east and 35 degrees north, that's a spatial relation. In this region, you have a green belt with trees. And the moment you start having the trees, how old are these trees, how many are they, which species this is an attribute relation. And that's something which we all have to have a clear-cut picture in our mind. And maybe we would have collected that data using high resolution imageries today, maybe a GOI image, maybe a Cartosat image and all that. So, what is important for us to see that? There are three properties which are important: locational properties, metric properties, that is geometry, and topological properties, LMT, locational properties, metric properties, topological properties, and they lead to thematic properties. Topological properties are expressed by information about example relations of neighborhood. What object is in the neighborhood? Containedness, does an object contain either objects? Overlap, is an object overlapped by other objects, etc. In addition to geometric and topological properties, thematic properties are also assigned to each object and they are stored in tables. The geometric and thematic information affect each other, obviously. These so-called objects are subject to temporal changes. Of course, we can do a change detection also through this. And based on above properties, the approaches that are used for performing a query could be threefold again. One of them could be a thematic query based on a single or particular theme. For example, a query could be select all rhododendrons from the image given, or select all springs located in the given spatial unit, select all wells. Second could be geometric query, where selection is based on a particular query related to a geometric parameters, as for example, select all the industries that are located less than 100 meters away from the river Ganges, or select tobacco shops located within 100 meters of any schools. We have learned the first one. Now, let us talk about the geometric parameter, and this query can be related to that. And for example, select all the industries that are located less than 100 meters away from the river Ganges, or select tobacco shops located within 100 meters or they are located near schools. And the third could be a topological query, simple topological modeling base, where the conditions criteria related to the surrounding spatial parameters and spatial relation is considered. In other words, selection of all objects based on particular spatial relations that achieve certain conditions. For example, select all the buildings that are lying in seismic zone 4. That is the one. So, now let us talk about another thing, that are the queries based on the coverage of the data sets. So, that was one that we learned just now, based on location, geometry and topology. Now, data sets are also, are also based on accessibility. The queries can be based on the coverage of the data set. How much is the coverage? Is it the total coverage we are talking about, or it is a subset of this data that we are considering? So, we have a query that is covering all, and we also have very important thing is subquery. Generally, we have subquery. Subquery is a select statement composed of 3 parts. Table 1, and the part of the subquery, in case if you have a look at it, in this table is clearly given. So, the first is the one that consists of comparison predicate and a comparison operator. One finds that in the comparison operator compares the comparison predicate with the outcome of the subquery, and the parts of subquery are also the expression. This impacts the result of the subquery. It is searched by the resultant query. And the third one is SQL statement. It is the usual format of the selection statement, and in parenthesis it is the usual format of the select statement and in parenthesis. That is something which is so very important. So, what have we learned? We have learned just now that there is a query, and we also have something called subquery, selected range of data. And what is important in that is your expression. What is important in that is your SQL statement. Let us now come to the third classification of the queries. It is query based on the access and result. We have either a direct query, or we have the query that deals with the manipulation of data. Now, let us learn this. What is a direct query? Direct queries, the data are accessed interactively by the user or by an application program. Thus, what we find is that the original data, through original data, there are commands, and those command lines or query masks are used, sequences of command lines, batch and the macros, and the format query language, SQL2 structured query language is used. And on the other hand, whereas queries could be based on by manipulating new geographical information or elements can be created, and these new elements can be used for analysis purpose in further steps. In general, the new objects have to be previously conceptualized model, and the data structures has to be implemented in the GIS. And some GIS can generate a minimal data structure without thematic attributes. Automatically, new information can be generated combining different objects, you will agree, and they can be used for further analysis. And there are different types of queries. And the GIS stores spatial and attribute data, we know by now, in two separate files, and these are recorded in two different tables. A map of a property parcel boundary and the corresponding data, such as the name of the owner, structure and the value of their structure, are linked by an identification number. And this allows the GIS to search and display attribute data based on spatial criteria. So, what is important is that unique ID, and ID is very important. For example, a GIS user can point to a particular property and ask the GIS to retrieve and display the attribute data of that parcel. But they can also ask the GIS to locate the corresponding property parcel on the map by supplying a record in the attribute database. And in the table you find the list of the many relational operators, query GIS, relational operator and the spellings. You all know by now all those relational operators. What are these? You can use a sign equal to, which you know. It is also called EQ or equal to, greater than, GT, greater than. If you have greater than equal, we call it GE, greater than or equal to. If the sign is less than, so we call them less than sign, symbol, and then LT and the less than. If it is like this, equal, what does it mean? Less than or equal, LE. And in case, yes, now guess, if it's this and this, what does it mean? NE, not equal to. So, you just use that easily embedded in a software, just use that and use it. Then GIS also handles much more complex queries, and the relational operators are so important in GIS that they are used for all numeric attributes, text attributes and other data types. Relational attributes are listed in the given table. If you look at it, the users can define search parameters involving arithmetic and logical expressions by building a query statement. And again, the operators can be, which we have just learned, some of them can be that, some of them can be this. What is this? Plus, yes, minus, equal, less than, greater than, less than equal to, and the different, we can specify the value. Several query statements can be combined to perform a single query. So, all those things which are there can be combined together and ask a question. For example, how many structures in this region are for sale, and also at the same time with a price of rupees 12 lakh and above, or less than and in a specific location near a market. This could be a query in a DBMS format, and the processes can be done and we can get a result. So, what will GIS do? The GIS would then search its spatial data file to find these parcels and the coordinates, and finally it would highlight these parcels on the display of the property parcel map. On the other hand, GIS users can also describe an area on the parcel map and ask the GIS to retrieve the attribute data of all parcels that are within the specified area, and this area could be in any shape. Logical operators could be employed to narrow the search or even to specify which attributes to retrieve. SQL also provide many additional functions like aggregate functions for spatial analysis, and they include functions as depicted in the adjacent table. What are these aggregate additional functions in GIS? Simple, what you've been learning, and these functions are AVGE functional, the average, cont functions, the number, numeric, minimum, maximum data, standard deviation function, standard deviation of the population, sum functions, variance, covariance and variance of the population function. So, all these are also which can be performed through GIS. You have got a spatial query in GIS, and this relates to the characteristic of a spatial entity in geographical space, and it could be a point, line or polygon. Spatial queries are performed by creating a query set based on the spatial relationship of map features. Spatial operators in the queries define the spatial relationship that exists between map features, and most spatial operators overlaps, entirely contains, contained by, contains, contained by, terminates in, terminus of, passes through, pass through, and a boundary has boundary, touches, meets and spatially equal can be combined to answer complex spatial queries. Proximity operators can also be used, nearby, further, within, beyond, and they also all can be combined. For example, a region with disaster management agency might collect a database of all the locational addresses and classify them into seismic zone 3 and 4 and non-seismic zone areas by performing a spatial query. Another example is depicted in table where a graphical input image with unique IDs produces an output graphical image based on a spatial query raised and set of relationships established. Is it clear? Let us take it further. In a graphical representation, you know it. You've got a graphical image, that's an input image. Then you put a query. You ask which shape is it, say it's polygon. Then you say select from a parcel where a population is less than 1000. Then you get another output image. Or you ask a question where the trees are greater than 100, or where the parcels, where the schools are greater than or equal to 2. So, input image is 1. After you've given a query, you get an output image. And say for example, the floodplain in the text parcel map, you also get the same thing. First of all, the user would query for all parcels that are within the floodplain area using the entirely contains operator. Then what follows is that these addresses would be classified as flood-prone polygons, flood-prone areas. And the GIS would then be used to find all parcels crossed by the floodplain boundaries. And then in case depending on the scale that you may want, you may also get villages, you may get tehsils, you may get districts, you may get blocks, depending on what input data you have put, right? And they fall that what villages fall in the flood prone areas. If you do not have a flood village data, you will not get this. So, I hope it's clear. So, the remaining parcel would be entirely outside the floodplain and put into a non-floodplain category. So, in case if you have to send a grant, the decision maker would find this data very useful. They will send that extra grant to the region where you have flood prone regions, whereas all those which are non-flood prone, this extra grant may not be given. So, what you have is a disjoint operator also that can also be used to check identify the flood prone parcel, and you label it and you use it maybe for further development plans. In addition to this, GIS can also combine and compare or query sets in several logical ways. Queries that involve 2 or more query sets are called set queries. Set query operators, commonly known as Boolean operators, often include the following operations: union, intersect, minors and difference and so on. And when conducting a study to find impossible sites for a new industry, several query sets may be created to find locations that are not suitable. The first query set might identify buffer areas surrounding endangered habitats, another might identify all forested areas, another might show all flat areas, and another might indicate locations of completing the industries which are there. The query sets then could be combined using the union operator, and all areas on the map that are not suitable would be identified. The remaining area would then be examined for potential sites. Right? Is it clear? I hope it is. So now I think so by now we all are very smarter, and now we are ready to create a query layer. So what have we learned till now? We are almost at the end of the chapter. We have learned that there are a lot of ways that the queries can be put in a GIS environment and we can get the result. That is the power of GIS. But for this, your data input should be as detailed, as much as you want your output to be. So be smarter, ask your smart queries, and you get the result. So now let's learn about the creation of a query layer. Now the query layer has to be created, and in most software you get a new dialog box in the left corner. For example, in an ArcMap, the first and foremost step is finding a way and developing a connection to the database. What followed is the visibility of the list of tables. As you're working with different data types, check whether the specific data type is conducive and acceptable by the software you're using. Sometimes less common databases are not supported by software, so you export them. In that situation, there is needed to convert the existing data set into an acceptable format. I hope this is clear. Another important thing which we have already learned is the need for SQL syntax, and this should be used when building a query layer. A common example would be as follows. Select from, say, test India and the base India. This would result in a query layer containing all rows from the India table. Once the query is created, it must be validated. So validation is very important. During validation, ArcGIS attempts to determine the properties of a query layer based on the first row returned in the table. The properties of a query layer are the following, and that's going to be so important. It's important to understand the properties of a query layer, because what we find is that all of them are generally identified by the unique identifier field. This is one of the many fields used by any software, ArcGIS also, uniquely defined layer and dimensionality, and this determines whether a layer's coordinates are included M values to store root data, or so and so the different types of data, geometric data, and so on, the point, multi-point, polygon, lines, and so on. And this is the coordinate system. What type of coordinate system? All of them are structurally stored. This means that all our work is generally done in the query text box. Therefore, it is essential to give a meaningful title to the query text box so that it can be recognized easily. This is to be followed by giving a relevant and required SQL query in the query text box. Next to follow is the validation. Once the query is created, it must be validated. Click validate to make sure that the query syntax is correct and returns data that can be used later on by that software, ArcGIS in the case, a present example. The validation process executes and the database and whether the result set from the query meets the data modeling standards enforced by ArcGIS is so important. A query layer is not added to ArcMap until it is valid. Rules for result are set for validation is as follows. Number one, at most one spatial field, at most one spatial reference, only one shape type, right? So that's important. And during the validation process, the dimensionality, geometry type, spatial reference, SRIT, and unique identifier properties on the query layers are all considered. And these values are based on the first row returned in the query. If you need to change these settings, you can do so through the advanced options available in your dialog box. Consequent of a query being successfully validated, generally there is a need to click finish or end depending on the software and add the result set, say in the ArcMap in the present example, as a query layer. Advantages of the query further enhances when we use it fully recognizing the power of GIS. Obviously, since GIS visualizes all queries related to where, when, what and why, possibilities can be enabled in GIS software. Since GIS enables to create a comprehensive framework to a concern in hand and supports the policy and decision making to arrive at the right ground reality, all queries related to the simulation and predictability can be addressed as GIS predict events. outcomes derived based on multi-criteria analysis carried out using the appropriate thematic layers in GIS. Even at the time of quick decision making, correct queries can assist in planning strategies, especially useful in cases where disastrous events demands quick decision making. Correct queries helps in geo-visualization of the present scenarios and how the simulation would look like, and this consequences such scenarios great assist the disaster management to plan for further and save human lives. So that's something. So what have we learned till now? We have learned till now that query building, query GIS is the most important part of GIS. You can ask anything from GIS provided your input database is strong. When, why, where? All the questions, predictability, all can be done, and this is something which you've learned just now. So in brief, we can say that the spatial information system deals with tools, algorithms and technologies in a computerized environment through innumerable queries. Queries enable handling of large data set and conversion of raw data into useful information. Another thing that we learned is that we can have simple query, we can also have a complex query. We can have a simple query which could be simply retrieved, or we can also manipulate a lot of queries. We can mix a lot of properties, locational properties, metric properties, tautological properties, and we can establish a query. Most of the time, what we have to keep in mind that depending on the objectives, subqueries which are there generally have three parts, and we all should know it. Part description, expression and SQL statement. If it is correct, nobody can stop us in making correct decision making. SRID is a layer spatial reference identifier and is used to ensure that only geometries with the same spatial unit and combined with the validation gives us a correct output. I think so that you all enjoyed today's lecture and you've learned the power of GIS also. Try framing good spatial queries. Try creating great database structure so that smart query can be asked and a correct spatial decision making can be done. Not only by you, but all those development agencies, all those people, the one who are there to bring this society or make this society a better place. During this climate change, climate variability, what is happening, GIS is such a strong tool. Through this query identification and through this query GIS can give you so many right answers. Please use this tool. Ask your friends to use this tool. Make correct queries and make this world a better planet. Thank you very much. I enjoyed this and I hope you also enjoyed it. Thank you once again.